So now we have different sets of complete wave functions for different sets of quantum numbers L and M, and we saw that the value for psi 0 0 0 0 represent L is equal to 0 and M is equal to 0. The first quantum number represents L and the second quantum number represents 0. The second quantum number represents M. Okay, so psi 0 0 is equal to 1 divided by 2 root pi. Now there you can see that it is independent of theta and phi, independent of any angle. So it means that it is spherically symmetric, means you are going to see the value of this function over the entire range of theta and phi. You can see that for any value of theta and phi, this function's value will be a constant. It means that over the surface of the sphere, this function will have the same value at every point. So this is a spherically symmetric function. This is a spherically symmetric function. Spherically symmetric function. So the plot of this function will be like this. So since it is spherically symmetric, you can have the axis is the axis, x-axis and y-axis here. This function will be like a sphere. This is not a ring, it's a sphere. Okay, and this function is this function can be plotted like a sphere. Okay, and the next function, that is psi 1 0, this psi 1 0, and you can also see there are other two functions, psi plus and psi minus, and these functions are trigonometric functions. They are in terms of cos theta, sin theta, cos phi, psi phi, etc. Okay, so these trigonometric functions, it indicates that the function will have some harmonicity as it contains the trigonometric functions. So these functions are called spherical harmonics. Spherical harmonics. So these spherical harmonics are these real functions in terms of which consists of the trigonometric functions which represent certain harmonicity of the wave function over the surface of the sphere. Okay, so spherical harmonics. We can try to plot these spherical harmonics. First let us take this function, that is psi 1 0, psi 1 0 1 0. And the value of psi 1 0 is equal to 3 by 4 pi raised to half cos theta. We can check how the value of this function varies with respect to different values of theta. You already know that theta is the angle from the z-axis, the plus z-axis, strictly saying. Okay, in the plus z-axis, theta is equal to 0, and in the minus z-axis, theta is equal to 180 degree or pi. And the xy plane, which is perpendicular to the z-axis, theta is equal to pi by 2 or 90 degree. So we can check how the function varies varies over the entire values of theta, that is from 0 to pi through pi by 2, or from plus z direction to minus z direction through the xy plane. So when theta is equal to 0, theta is equal to 0, then the function will get its maximum positive value, because cos theta's maximum value is 1 plus 1, and the cos theta get the value 1 when theta is equal to 0, cos 0 is equal to 1. So the function gets its maximum positive value when theta is equal to 0, and theta is equal to 0 means it is in the plus z axis. Then in that case it gets the maximum positive value. The function gets the maximum positive value. What is that maximum positive value? That is 3 by 4 pi raised to half into 1. That is 3 by 4 pi raised to half. And what about when it reaches theta is equal to pi by 2? Theta is equal to pi by 2 is in the that's in the xy plane. Theta is equal to pi by 2 is in the xy plane. In the xy plane, the function becomes 3 by 4 pi raised to half into cos pi by 2. Cos pi by 2 is equal to 0. Cos 90 is equal to 0. So the function's value becomes 0. And when theta reaches pi, that is the maximum value of theta in the polar coordinate system. So when theta reaches pi, the pi is in the theta is equal to pi is in the minus z axis, and when theta is equal to pi, the function becomes 3 by 4 pi raised to half cos pi, that is equal to cos pi is equal to minus 1. So the function becomes minus of 3 by 4 pi raised to half, that is the maximum negative value. So we have seen three situations here. Means when theta is equal to 0, that is in the plus z axis, the wave function has its maximum positive value. When theta is equal to pi by 2, that is in the xy plane, the wave functions become 0. And when theta is equal to pi, that is in the minus z axis, the wave function gets its maximum negative value. So it means that the wave function's maximum values are in the plus z direction or in the minus z direction. Either it is maximum positive value or maximum negative value. Okay, that is in the z direction. Perpendicular to the z direction, there is xy plane, but in that xy plane, the function becomes 0. So when we are plotting this one, it will be like this. We can plot this one. Actually, we have to plot this in the polar graph. I will explain this in another video. Not now, because we are going to learn the hydrogen atom, thus Schrodinger wave equation, solving Schrodinger wave equation for hydrogen atom, the complete quantum mechanical treatment of the hydrogen atom. There we will see how to plot the functions in polar graphs. Then I will explain how to plot this in the polar graph in detail. Now we will simply plot this. Okay, so let me draw the z axis here. This is z axis, that is plus z axis, and this is minus z axis. The coordinate originate here, and this is x axis, and perpendicular to that there is y axis. Okay, and our function gets the maximum positive value in the plus z axis, that is here, that is the maximum positive value. And when it reaches the xy plane, its value will continuously decrease, means the value will be decreasing like this. Okay, it will decrease like this. And when it reaches the minus z direction, the value will again increase, but in the negative direction. Okay, the negative value will increase. It will be like this. And that is how we plot the function in the coordinate system. And you have to note here that it depends only on theta, not on phi. Phi is the angle on the xy plane. Phi represents the angle from the plus x direction. So if you are rotating these half circles about the z axis, perpendicular to the xy plane, or over the entire range of phi, then since it is independent of phi, the circle is not going to change. It means that this semicircle will rotate about the z axis over the entire range of phi without any change in the value, because it is independent of phi. So what will happen if you are rotating this semicircle perpendicular to about the z axis, then what will happen? You will get a sphere, right? You will get a sphere. And the sphere, these two spheres you will get, one sphere will be above the xy plane and another sphere will be below the xy plane, and both spheres will have a common axis, that is the z axis. So the function will be two spherical lobes over and below the xy plane, oriented through the z axis. Two spherical lobes oriented through the z axis, perpendicular to the xy plane. So this is analogous to the pz orbital that you have already learned in your lower classes. You have only learned the shape of the pz orbital so far. You haven't learned so far how the shape of the pz orbital is being derived, but you will see that later. but I'm just bringing your attention to what you already know about the PZ axis. You know that these are also two lobes, one above the xy plane and the one below the xy plane, and both lobes are oriented through the z axis, and this is also analogous to that. Two lobes are there, they are oriented along the z axis perpendicular to the xy plane. Okay, and that is how we plot psi 1 0. That is analogous to the PZ orbital. Analogous, it is not same. Okay, I am just saying it is analogous. And now we will see how to plot the next function, that is psi plus. How to plot psi plus function. Psi plus is nothing but 3 by 4 pi raised to half sine theta cos phi. 3 by 4 pi raised to half sine theta cos phi. So we will see what will happen over the entire range of theta and phi. You have to note here as that both psi plus and psi minus depends upon both theta and phi, but psi 1 0 was depending only on theta. Here it depends on both theta and phi. So we have to look into that in more detail. So let us take the psi plus function, and we will see when the psi plus function get its maximum value. Psi plus function get its maximum value. So let us look into the first part of the trigonometric function, that is sine theta. Here sine theta, and sine theta get its maximum value when theta is equal to pi by 2, right? Theta is equal to pi by 2. When theta is equal to pi by 2, sine pi by 2 is equal to sine pi by 2 is equal to 1. That is the maximum value of sine theta. So this function will get the maximum value in terms of theta when theta is equal to pi by 2. Okay, theta is equal to pi by 2 is in the xy plane. We already know this. Theta is equal to pi by 2 in the xy plane, like here. Okay, xy plane. So the psi plus function will have its maximum value in terms of theta in the xy plane. And now we can look into the next part, that is cos phi, sin theta cos phi. Next part is cos phi. So when cos phi will get its maximum value? Cos phi get its maximum value when cos phi is equal to 1. Cos phi is equal to 1 when phi is equal to 0. Means when phi is equal to 0, cos phi is equal to 1, and then there is a maximum positive value. Okay, in terms of phi, that's a maximum positive value. And that is along the x-axis. Phi is equal to 0 means it is x-axis, plus x-axis, plus x-axis. So in the plus x-axis, it gets this maximum positive value. And if you are looking into the next direction, that is phi is equal to pi. Phi is equal to pi is in the minus x-axis. When phi is equal to pi, then cos pi get its a maximum negative value. Cos phi is equal to minus 1. So maximum negative value in the minus x-axis. So this function get its maximum positive value in the plus x-axis, and this function get its maximum negative value in the minus x-axis in terms of phi. We already saw that this function has its maximum value in the xy plane in terms of theta. In the xy plane, either it can be in the x-axis or it can be in the y-axis or somewhere in between x and y-axis. We are checking where it is. Now we also that in the x-axis it gets its maximum positive and negative value. We can check what happens in the y-axis also. In y-axis, phi is equal to pi by 2. Phi is equal to pi by 2 in the y-axis, positive y-axis, right? And then it becomes cos pi by 2. Cos pi by 2 is equal to cos pi by 2 is equal to 0. It means that in the y-axis, in the plus y-axis, the function has no value. It becomes 0. And what happens when phi is equal to 3 pi by 2? 3 pi by 2 is nothing but the minus y-axis. And cos 3 pi by 2, that is equal to cos 3 pi by 2, that is equal to 0. It means that in the minus y-axis also, the function becomes 0. So what we have seen so far, the function is having the maximum value in the xy plane from this from the theta consideration, and in the xy plane we were checking whether it is in the x-axis or in the y-axis. Then we saw that it is in the x-axis, it has its maximum value. In the plus x direction it has its maximum positive value, and in the minus x direction it has its maximum negative value, and in the y direction it doesn't have any value, the function vanishes. And what about the z-axis itself? In the z-axis, theta is equal to 0. Theta is equal to 0 means we have sine 0. Sine 0 is equal to 0. It means that in the z-axis also this function has no value. In the minus z-axis, that is z-axis, okay, in the minus z-axis, theta is equal to pi, then sine pi is equal to 0. It means that in the minus z-axis also this function doesn't have any value. So what does it say? It says that this function has its maximum value in the x-axis, in the plus x direction and the minus x direction. We will have a similar plot like this. So let us plot it here. This is the z-axis, and this is minus z, and this is the plus x-axis and plus x-axis, and this is minus x-axis, and this function will be like two spheres. When you are considering the entire ranges of theta and phi, you can see that these are two spheres. It is not confined to one plane. These are two spheres oriented through the x-axis. These are two spheres oriented through the z-axis, but this function is two spheres oriented along the x-axis. So you have a positive lobe here and you have a negative lobe here also. Okay, so this is how the next function is plotted, and this function is analogous to the px axis. You have already learned the shape of the px axis, right? So there also we have two lobes with a positive and negative sign oriented through the x axis. Here also we have the wave function having two lobes, spherical lobes oriented along the x axis. And this is how that function is plotted. Now we have the third function, that is psi minus. Psi minus is 3 by 4 pi raised to half sine theta sine phi. Only difference is here. With respect to psi plus, the difference is only here, sine phi, in sine phi only. So we can only consider what happens in terms of phi. So you know that when phi is equal to pi by 2, then sine pi by 2 is equal to 1. That is the maximum value of sine phi. So maximum value of sine phi is obtained when phi is equal to pi by 2, and phi is equal to pi by 2 is in the plus x axis. And what about the phi is equal to the next maximum negative value? That is when phi is equal to 3 pi by 2. Then sine 3 pi by 2 is equal to minus 1. So that is the maximum negative value. So this function psi minus has the maximum positive value and its maximum negative value along the y-axis. This is the y-axis. Oh, I wrote x-axis? No. Y-axis. That is the y minus y-axis. Sorry. So this is oriented along the y-axis, and this function was oriented along the x-axis, and this function is oriented along the y-axis. Phi is nothing but the angle from the x-axis. So in the x-axis phi is equal to 0. When it turns 90 degree, it reaches the y-axis. That is why this y-axis here. Okay, so psi minus is oriented along the y-axis. So if we are plotting the psi minus, then we have the plots like this. Okay, this is z-axis, and this is x-axis, and this is y-axis. So along the y-axis there will be two spherical lobes, and it will have positive, one lobe will have positive and other lobe will have a negative sign. And that is how the psi minus is oriented, and this corresponds to the py orbital. It is analogous to the py orbital. It is not the py orbital. What we are learning now is a particle on a sphere. It is not an atom. Okay, so but there is a wave function, and that wave function is oriented along the y-axis in this case, and that is analogous to the py orbital that we are going to learn soon. Okay, so we have the functions plotted along z-axis, x-axis, and y-axis, and we have another function which is spherically symmetric, and this corresponds, this is analogous to the s orbital. So why we are learning this system? This is a hypothetical system, that there is a particle on the surface of a sphere. That was a hypothetical system. We put the potential energy of the particle as 0. This was put like that just to make our life easy, right? Because we are going to learn with the system, we are going to deal with the system, and if the potential energy has some value, then solving the Schrodinger equation becomes more tedious, and we put v is equal to 0 so that the Schrodinger equation becomes simpler and we can easily solve the equation. So we set up a hypothetical system like this, and initially we asked why we have to learn this type of system. Now you know why we have to learn this type of system. From this system we get some results which are analogous to the real situations, like orbitals in the atoms. Okay, so we are building only a step, and through this step we are going to enter our real picture or real scenario, that is about the hydrogen atom, that is the simplest atom, right? So with this basics, next we are going to enter into the world of quantum mechanics of a real atomic system. For us chemists it is very important, and we will learn that system in detail, and there we will derive the expressions for different orbitals, and then we will plot the orbitals in the polar graphs, and we will see the energies of the orbitals, and we will have a fantastic experience when we are learning that one. What we have done so far is that we created some hypothetical systems, and we learned how to solve these systems, and now we have a good basic to deal with the real systems, right? So I wish you all the best. By wishing all the best, I am not going to stop this lecture series here. I am going to wish I wish the best to you all, because now we are going to stop this simple systems or hypothetical systems. Now our task is to deal with the real systems. That is, we are going to learn the hydrogen atom in detail, and so I request all of you to go through this basics stuff very thoroughly. Okay, if you have missed this lecture series, all the lectures are uploaded in YouTube. Go back to my lectures and go through each and every step, and take your notebook, and when you are watching this video, you write it in your notebook also. If you have any doubt, pause the video there, and then you watch it again. Okay, or if you have any doubt, you can call me, or you can text me, or you can send a message in the WhatsApp, or you can type the comment below the YouTube video. I will answer in all ways, and what you have to do now is to go through all these videos. Means I would recommend you to go through the entire quantum mechanics that we have learned so far through the two semesters. If you don't have enough time for that, at least go through the quantum mechanics of this semester itself. We started with particle in a ring, and that was a basic for dealing with the particle on a sphere, and now we have learned the particle on a sphere in detail, and now we are in a position to enter into the hydrogen atom. Okay? Enter into hydrogen atom doesn't mean that we are going inside the hydrogen atom. What I meant is that we are going to enter into the complete treatment, or we are going to deal with the complete quantum mechanical treatment of the hydrogen atom. So these basics are very much necessary, especially the polynomials that you have learned so far. Okay, so go through this lecture series very thoroughly, and then we will learn the hydrogen atom.